All right, our next example, example 2, we are to determine the volume of a cone, so a circular cone, with height h and radius r. So I'm going to go ahead and just assume that our cone is with the tip pointing upwards. So in our bottom plane, our y equals 0 plane, we would have our circle like that, and then going upwards. Okay. But let's go ahead and make this a little bit bigger. So let's go ahead. We've got a little bit of perspective here. And I guess I want that to curve up a little bit more. There we go. It's a little better. Okay. My goal was to try to get this above the center of the circle. Okay. And I guess we can sort of make that look like it's in the background. Okay. So there's our right circular cone. We know it has a height of h and a radius r. So I'm going to go ahead and just draw a center line down to the center, roughly speaking, of this circle. This distance here would be h, and then the radius of this cone would be r. So if we call this bottom plane where the base of our cone lives, so if we treat this as sitting on like a tabletop or desk or something, then this right here would be the bottom. So this is the y equals 0 plane. And this here, we can just think of this as the y-axis moving upward. Okay, so what we want to do is consider a slice. So imagine some intermediate little slice of this cone. Well, we know that it would be a circle. So we know the radius of this, we know the area of a circle is whatever this circle's radius is squared times pi. So what I'm going to do here is I'm going to choose to call this distance, I'm going to call this distance x. Okay, so this is x. Then this means that the area of the circle is pi times whatever the radius is, which in this case we're calling it x. So that's pi times x squared. And if you watch the previous video on example 1, you will recognize that it's more or less similar triangles yet again. So we really have these two triangles, the big triangle, and then we have the small triangle, and we want to go ahead and relate them. So I won't color code things this time with the triangles. I'll just, as I did in the last video, I'll just draw all of these triangles. There's the, let's call that the big triangle. We don't need to waste a lot of room here. Let's just say that this is the small triangle then, and that they are similar triangles. Well, the big triangle, we know its height is h, and its base, which is really just the radius of the base circle, is r. Then, for our little or smaller top triangle, the base of the triangle is x, which is the radius of that circle. And now we need to figure out what this distance is. Well, in order to do this distance, let's go ahead and assume that this circle that we have drawn here, let's say this was drawn at some distance y. So you move up some amount of some distance y. This y, again, is going to be some fixed value. It's somewhere between 0 and h. You can think of the top here of this cone, that this corresponds to the line y equals h, and this line here that corresponds with the bottom, this is y equals 0. So we are just at some intermediate y value. So if this full distance here is h, and this smaller distance here is y, then that forces this distance here to be h minus y. So here we have h minus y. And from here we can get our similar triangle relationship. So h minus y divided by x is equal to h over r. And we really want to solve for x because this area function, we would like to express this as a function of y, because when we move in the y direction, all the cross sections are the same size. They're all circles, but what's changing is the radius. So the area should be a function of the height y. So I would solve this for x to get r over h times the quantity h minus y. And then we can import that. So the area as a function of y is pi times x squared. So this would be pi times r squared over h squared times h minus y quantity squared. So the volume of this cone is the integral from 0 to h, from bottom to top, of our volume. So let's remember here that r and h, as well as pi, of course, they are all constants. So we can actually write those outside of the integral. So this would be pi r squared over h squared. And then we would have h minus y quantity squared dy. Now last time in video 1 we had an integral that was very similar looking, and we did a formal u substitution on this. But notice the inside function is linear. It's a first degree polynomial. So we can really just integrate as if this were just the variable by itself, but then we'll have to compensate by dividing by the derivative of this inside function. So the derivative of the inside function is -1. So our answer would be -1. So -1 times that pi r squared over h squared. And if we integrated this, we would get a 1/3 and then that variable, that quantity cubed. So it's in this way that we can sort of avoid the u substitution. As you progress through Calc 2, and certainly when you get to Calc 3, these kinds of integrals are just done real quick. No work or explanation even said. So we can evaluate this now. So if I plug in h, let's see here. Notice that if we plug in h, then this is 0, and this whole quantity is 0. So really, the only thing we're going to get that's non-zero, ironically, is when we plug in 0, because the inside becomes h minus 0, which is h. So this would be top bound plugged in yields 0, minus the bottom bound plugged in. Well, we've got a negative here, and we're subtracting it, so this gives us a double negative, so plus pi r squared over 3h squared. I'll go ahead and move my 3 over here to be with the h squared. And then we just have h cubed. And of course, 2 of those h's will cancel. We'll have 1 left over upstairs. So we should have the hopefully familiar formula for the volume of a cone, and that is pi r squared times the height over 3. So 1/3 the area of the base circle times the height.